Okay, I want you to imagine a regional power grid for a second. It's, autonomously adjusting its voltage to match this incoming, totally unprecedented winter storm.
Right. Highly critical situation.
Exactly. So thousands of sensors are feeding data into an artificial intelligence, and this AI is actively balancing the load so hospitals stay online, homes stay warm. But then imagine that AI hallucinates just a single data point.
Oh, wow. Yeah.
Right. It makes this probabilistic guess that is mathematically wrong, and before a human operator can even blink, 3 substations catch fire. I mean, we aren't talking about a bad chatbot generating a picture of a guy with 7 fingers anymore.
No, not at all.
The era where, an AI making a mistake is just this funny screenshot you share with your friends, that is entirely over.
It really is. The stakes have shifted completely, mostly because the environment is no longer contained to a browser window on your laptop.
Right.
We're in the middle of this massive technological leap. I mean, autonomous AI agents are being plugged directly into physical critical infrastructure. We're talking power grids, industrial control systems, aviation, financial markets.
It's stuff that runs the real world.
Exactly. And when you hand the keys of the physical world over to a probabilistic reasoning engine, well, an unconstrained error doesn't just cause software friction. It causes actual service blackouts, cascading financial contagion, and, like you said, catastrophic physical damage.
Which means that old Silicon Valley mantra, the whole move fast and break things idea.
Yeah, that doesn't fly here.
It's essentially a death sentence in this context. You cannot move fast and break a regional power grid. And honestly, that brings us to the core mission of our deep dive today.
It's a fascinating shift to look into.
It really is. We are unpacking the terrifying but also thrilling reality of how engineers are actually attempting to put a fence around an AI. Because you can't just let a large language model directly pull the levers of a drone swarm or a power plant.
You'd be asking for a disaster. So the industry is pivoting to this very specific, highly rigid architecture designed to guarantee safety. It's a complete paradigm shift away from open-ended execution.
Okay, let's unpack this, because the architecture here is just wild. We are trying to marry 2 very different concepts, right?
You have a probabilistic AI that guesses based on statistical weights and a physical system that requires absolute mathematical certainty.
Exactly. So to explain how this fail-safe framework operates without getting super bogged down in the jargon, think of it like a bowling alley, but a bowling alley functioning at light speed.
Okay, I like this. A bowling alley.
Yeah. So in this setup, the artificial intelligence, the reasoning engine, is the bowling ball.
Yeah.
It's just trying to find the best, most efficient path down the lane to knock over the pins. That's the AI trying to generate an action.
Right, it's just doing what it's trained to do, finding patterns to reach a goal.
But you don't just let the ball roll wherever it wants. You have a state verifier. Think of the state verifier as a sensor that checks the bowler's stance before the ball is even released.
Oh, that's a great way to put it.
Yeah, it's mathematically checking if the operational state, like say the thermal threshold of a power transformer, is actually within valid bounds before anything else happens.
Right, establishing the absolute reality of the environment at that exact millisecond. And then, once the ball is rolling, you have the deterministic guardrail.
To heavy iron bumpers.
Exactly, the bumper lanes. These are the physical, uncompromising boundaries. If the AI proposes an action that violates safety protocols, like sending too much voltage down a line, these guardrails don't ask the AI to reconsider.
Right, they don't prompt the LLM and say, "Are you sure?"
No, not at all. They act like gravity. The guardrails are hard-coded, inflexible policy layers. They physically bounce the decision back into a safe zone, overriding the neural network entirely.
The AI just cannot bypass the physics of the bumper.
What's fascinating here is how these systems handle a total loss of control. I mean, what happens when the ball keeps hitting the bumpers over and over?
Right, if the AI just keeps hallucinating bad ideas.
Yeah. If the reasoning engine keeps proposing dangerous actions, or if the telemetry data shows the system's state is drifting into an anomaly, the system has this built-in circuit breaker. It initiates a protocol called graceful degradation.
Graceful degradation. I love that term. So it doesn't just blue screen and crash?
No, it automatically steps down the level of autonomy. If the AI model's internal confidence drops, the circuit breaker instantly strips the neural network of its control.
It just kicks the AI out of the driver's seat.
Automatically. And it falls back to classical algorithmic control. Or if it's really bad, it triggers an immediate human-in-the-loop escalation. It locks the system down until a human operator takes the stick.
Wow.
And a crucial detail here, the system maintains immutable audit trails.
Meaning everything is recorded?
Everything, every raw observation, the intermediate chain of thought from the AI, the verifier checks, it's all stored in tamper-evident storage for regulatory auditing.
Okay, so having this incredibly secure bowling alley structure sounds great in theory, but where exactly is this highly guarded AI actually driving the ball? Which brings us to the specific domains adopting this.
And this is where the stakes get very real.
Right. And I have to play devil's advocate for the listener here. If these guardrails and circuit breakers are so airtight, why are we still so nervous? Like, what is the actual worst-case scenario if this control loop fails?
Well, let's walk through the specific domains from the research, because the failure impacts are drastically different depending on where the AI is deployed. Let's start with cybersecurity, like a Security Operations Center or SOC.
Okay.
The intended goal there is the autonomous isolation of compromised endpoints, stopping hackers at machine speed.
Right, but wait, if every single proposed action has to be routed through a state verifier and evaluated against these heavy guardrails, aren't we adding massive latency? Doesn't that slow the AI down too much to fight a cyber attack?
That's a common concern, but actually, the latency of a deterministic check is magnitudes lower than the neural reasoning itself.
Oh, really?
Yeah, evaluating a hard-coded math limit like if X is greater than Y, block the action that takes microseconds. The neural network is what takes time. So the guardrails are just a lightweight, high-speed filter.
Okay, makes sense. So what's the worst case scenario there?
Well, if the loop fails, or if you don't have good guardrails, the AI might get overzealous. It sees a false positive threat and decides the most efficient way to protect the network is to accidentally shut down your core enterprise services.
So it paralyzes your own infrastructure to save it.
Exactly. But that scales up terrifyingly when we move to energy and power grids.
Like the winter storm scenario from earlier.
Right. There, the AI handles real-time parameter tuning and load balancing. A failure doesn't just mean the lights flicker. It means you alter the phase synchronization of the grid.
Which means?
Physical transformer overloads. The copper inside literally melts. And when one transformer trips, the power surges to the next one, overloading that one too.
A domino effect.
Exactly. A cascading frequency failure resulting in a regional blackout. All because a neural network made a bad statistical guess.
And if an AI can physically melt a grid, it can definitely crash the economy.
Which brings up financial markets. I mean, we've had algorithmic trading for a long time, right?
We have, but those traditional algos are deterministic. They follow strict if-then rules.
They only do what they're explicitly told.
Right. But these new autonomous agents are managing risk based on open-ended reasoning, sentiment analysis, real-time geopolitical data. If the loop fails here, a flash crash isn't just a dip. It could trigger systemic market contagion across multiple institutions before a human even realizes what happened.
Okay, that's terrifying. But then we have aerospace and defense. Yes, and this is where the system faces the most adversarial environments possible. They focus on swarm coordination and jam-resistant edge execution.
Jam-resistant meaning like a fleet of drones operating where their signal to home base is completely cut off.
Yes, they have to make tactical decisions on their own. And if a state verifier misinterprets a sensor reading there, the failure impact isn't just losing a vehicle, it's unintended escalation.
An AI hallucinating a hostile target.
Exactly. Engaging based on a probabilistic error in a contested area.
Okay, hearing about unintended escalation and transformer overloads, it naturally prompts this realization. Standard software engineering rules just aren't enough to prevent these disasters, right? If the stakes are this apocalyptic, the traditional ways we test software must be fundamentally broken when it comes to AI.
They absolutely are. And if we connect this to the bigger picture, this is the core of the technical dilemma with certification.
Right. This is what the sources called the non-determinism dilemma. Let's break this down for the listener. In traditional safety engineering, like aviation software, everything is deterministic. Input X, get Y.
Yes, the DO 178C standard in aviation, for example.
Yeah.
You can test it exhaustively until it's mathematically proven to never deviate.
But neural networks are probabilistic. So how on earth do you formally certify a system when identical environmental inputs might yield a completely different action on a Tuesday than they did on a Monday?
You've hit on the biggest open research challenge today. You can't just trace a billion-parameter neural network back to one line of code. It's impossible. And there were two massive hurdles here. First is distribution shift and edge cases.
Which is when the real world throws something at the AI that wasn't in its training data.
Exactly. What happens when the AI faces an unprecedented extreme weather event on that power grid? It might not just crash. It might produce an uncalibrated high-confidence hallucination.
Confidently wrong.
Dangerously wrong, but it thinks it's 99% correct.
And the second hurdle.
This is the part that is just fascinating from a systems perspective. Emergent swarm dynamics.
Oh, this is the multiple agents thing.
Right. When you have multiple autonomous agents interacting simultaneously, like in a multi-agent cyber defense, they create these unpredictable system-level feedback loops. Agent A reacts to Agent B's probabilistic guess, which changes Agent C's state.
It's just a compounding, chaotic mess.
It creates a state-space explosion. Proving mathematically that a dynamic swarm won't trigger unpredictable emergence is borderline impossible right now.
Which forces us to look at the physical reality of the hardware too, because to ground this back in reality, these systems have massive physical limits. We call them SWAP constraints, right? Size, weight, and power.
Absolutely crucial point.
Because an air-gapped defense system or a drone swarm doesn't have the luxury of pinging a massive, power-hungry server farm in the cloud. They have strict power budgets.
You can't put a liquid-cooled server rack inside a drone.
Exactly. So they have to use highly optimized small language models, or SLMs, running locally on the edge.
And when you shrink a model to fit on-edge hardware, you inherently reduce its reasoning capacity. It's faster, but it's statistically more prone to hallucinate or miss a complex pattern.
Which makes those heavy iron bumper lanes, the deterministic guardrails, even more desperately needed.
Precisely. We have probabilistic models, constrained by power, prone to unpredictable swarm behavior. And yet, we desperately need them to manage our physical infrastructure. A human just can't process 1 million grid sensors fast enough.
So this intense tension, needing the AI but fearing the AI, forces the industry toward a brand new hybrid solution.
And that ultimate goal is what the industry is calling certified autonomy.
Right. It's not about letting machines run entirely independent and unmonitored.
No, it's about marrying the brilliant, open-ended adaptability of deep learning with the guaranteed predictability of classical control theory and formal logic.
Which is huge for you, the listener, to understand.
Yeah.
Because this transition from AI being a fun novelty that writes your emails to the invisible manager of the power grid, financial markets, and aviation, it means the era of move fast and break things is well and truly over. We are entering an era of mathematically proven operational boundaries.
It's a fundamental shift in how civilization operates. But I want to leave you with a thought to mull over, building on those immutable audit trails we talked about earlier.
Okay, lay it on us.
Consider this scenario. What happens when the AI operates perfectly within its mathematically proven guardrails, but a catastrophe still occurs?
Wait, how would that happen?
Because the human engineers designed the wrong guardrails in the first place.
Oh, man.
Right. When the unalterable audit trail proves definitively that the AI did exactly what we constrained it to do, who takes the legal fall for the blackout? Is it the AI developer who made the reasoning engine, the safety engineer who hard-coded the salty guardrails, or the auditor who signed off on it?
Wow. We built the perfect bowling alley, but we pointed the lane at a crowd of people.
Exactly. When the math is flawless, but the human intent was flawed, where does the liability land?
That's a chilling realization. The most dangerous part of this incredibly advanced AI loop might still be the humans writing the rules. Well, that gives you plenty to explore on your own the next time you flip a light switch or board a flight. The invisible architecture taking over our physical world is an absolute marvel, but it is walking a razor-thin line. Keep questioning the systems around you, stay curious, and we will catch you on the next deep dive.